And we are live.
Hi, hello. I'm sorry we are a few minutes late due to technical difficulties. I'm very delighted to introduce Elizabeth Hunke. She's a scientist and the deputy group leader of the Fluid Dynamics and Solid Mechanics group at Los Alamos National Laboratory. She got her PhD originally in applied mathematics, but is now an expert for sea-ice and polar climate. Elizabeth leads the CICE consortium, an international group of institutions jointly maintaining and developing the CICE model in the public domain for research on operational communities. I have compiled the CICE model hundreds of times, but I am not totally sure how to actually pronounce the abbreviation. So I'm going to call it CICE for now, and I looked it up on the Wikipedia. She co-chairs the LANL Cross-Disciplinary Working Group on Energy and Climate Impacts, and is the LANL's Program Manager for the Department of Energy's Earth and Environmental System Science Program. As the talk continues, please post any questions in the chat, and then I will ask them over to Elizabeth. Thanks very much. We're very excited, Elizabeth.
Thank you, Judy. So I'll ask the host to cut out my video in order to save bandwidth. Thank you very much. And so, as Judith said, I am the primary author of the CICE model. You did pronounce that right. And in the past couple of years, we have set up a consortium to develop the model in conjunction with the broader community. And there are basically three overlapping communities of CICE modelers. There are the scientists that are interested in understanding and really accurately simulating the detailed physical processes at all scales. Then there's people like me, who are the climate modelers, interested in computationally efficient representations of large-scale sea ice characteristics and processes. And then there's the operational forecasting community, and they are interested in models that produce very efficient and skillful predictions for a range of spatiotemporal scales. The consortium includes members from all three of these groups, and although I'm primarily a climate modeler, I've learned a lot about forecasting needs. There is actually a fourth user community, and that's the policymakers and other stakeholders like that, such as mariners. So I'll begin by briefly explaining what CICE is, how it works, and why we care. The main issue between climate simulation and operational forecasting really is one of scale, both in time and in space. And so I'll give some examples of some new process-based CICE model developments that are relevant for operational forecasting needs. And then I also want to discuss the challenges and some potential solutions for using these large-scale models for operational forecasting. So first, sea ice is frozen seawater. It's different from land ice like glaciers and ice sheets, and that's because they are made out of snow. That snow is compacted into ice, but the sea ice is the frozen ocean. And sea ice floats at the ocean surface, and at any given time, it covers on the order of 4% of the Earth's surface. Now, sea ice's vertical thickness or depth is much smaller than its horizontal extent. Young, undeformed ice is generally 1 or 2 meters thick at most, but sea ice is often deformed into ridges, like you see in this picture behind Steve Ackley, and it's usually less than 10 meters thick or so. Now, in addition to being three-dimensional, sea ice is in motion. So this is a video of ice near Svalbard, and we climate modelers do not try to model the motion of the individual ice flows, but we do try to capture the larger scale patterns of ice motion across the basin, and that's what's in the illustration in the upper left. So as it's moving around, wait, I need to get my slide to advance. As it's moving around, the ice is carrying things with it, like the vertical heat and salt profiles. It carries snow, it carries liquid water, also soot, dust, algae. It carries an age, you know, it has a certain age, and so on. And these things can affect the ocean and the ecosystems below or the weather above. So sea ice is not pure ice. It has a lot of stuff in it, mostly taken up from the ocean as the ice freezes. This photo shows a layer of algae that has grown within the ice. And as you might imagine, the relatively dark colored algae absorbs sunlight and warms the ice's interior. That contributes to ice melting and disintegration. So what's important about sea ice really depends on what your interest is. If you're a biologist, it might be the hydrological properties of the ice that are needed to nourish the algae. But if you're an oil or a shipping executive, then it might be the strength of the ice. For a climate modeler, it's the albedo, or the reflectivity. The ice is very bright, but as more dark ocean shows through, like you see in this image, that ocean warms from the sunlight hitting it, and that warmth melts the ice, which exposes more of the dark ocean. So that's a feedback in the climate system. It's called the sea ice ocean albedo feedback. And the sea ice's albedo really is critical for the Earth's radiation balance. Sea ice has an outsized role in the climate system because it is so bright. We modelers try to get it right by representing as many of the processes that affect it as we can. The other thing that is critically important for climate is the ice volume, and the ice thickness in particular. The ice thickness determines the sensitivity of the ice to melting and freezing, and the ability of a model to predict the rates of future change of the sea ice pack depends at least in part on the ice thickness that the simulation starts out with. You can see that in the plot on the right. There's the bright green line kind of up near the upper right part of that plot. And that's the model with the thickest ice in this collection of models. And in the left-hand plot, it has the largest ice cover. SICE is sea ice concentration. And it keeps it through time. Whereas the thinner ice, like the bright blue one that's very thin on the right-hand side, tends to lose its sea ice concentration very quickly over time. So those were model results. And these are observations that show that the sea ice is definitely changing in the climate system, especially in the Arctic, where it has been by half since the 1980s. And the extent is also regularly well outside the range of variability, even up through 2010. So that's in the plot that's in the center, the upper center part of the slide. And there's two gray ranges, which are 1 and 2 standard deviations. And you can see that for a couple of recent years, the sea ice extent in the Arctic is well outside of those standard deviations. The reason I care about this is that the temperature gradient between the polar regions and the tropics is decreasing. And that's because the polar regions are warming faster. I don't have a cursor to point out things, but this plot is looking down at the Arctic. You might be able to see Greenland kind of toward the center. The continental US is just below that and to the left, with Alaska going on around. There's Alaska and Siberia, and back around to Greenland. That temperature gradient between the Arctic and the tropical regions is what keeps the jet stream moving. And you can kind of see the jet stream in this plot as the areas where the contour lines are very close together. But as that gradient decreases, then the jet stream begins acting more like a lazy river on a flat plain. So its lobes can actually get stuck in what meteorologists call a blocking pattern. And as you can imagine, the same weather for days or weeks on end in a local area leads to more floods or more droughts or heavier snowstorms and things like that. So that's really why we care about what's going on at the poles. I do want to tell you a little bit about the fundamentals of sea ice physics. And one of the most important concepts is that the thermodynamic growth and melt rate depends critically on the ice thickness. That's because it's a function of the gradient of the temperature with the depth or the thickness of the ice, which is Z on this plot. So thinner ice grows and melts much more quickly than thicker ice does. And I'm showing a general form of the heat equation, which says that the enthalpy evolves dependent on conduction, that's the first term on the right, and external forcing such as temperature at the upper and lower boundaries of the ice, as well as absorption of radiation in the interior of the ice. Now there are many different thicknesses of sea ice in a grid cell, and so to capture the large variation in ice growth and melt rates that you could see in a grid cell, like in the image at the left, we allow a distribution of sea ice thicknesses within each of those grid cells, and we put more resolution for the thickness distribution down where the thinner ice is. So in the models, we generally carry 5 thickness categories plus open water, and each ice category has its own snow, its own radiation budget, and its own thermodynamic calculation. And this essentially enhances the resolution of the column physics within each of the grid cells. The thickness distribution is a distribution in the mathematical sense. It is the fractional area of a grid cell that's covered by ice of a certain thickness. And this equation is the fundamental equation for the whole sea ice model because it is what integrates all of the different processes. It includes convergence and divergence of the ice, that's the first term on the right, as well as mechanical redistribution, which is what we refer to colloquially as ridging, and also the thermodynamic growth and melt. Now, climate models require the ice thickness distribution in order to capture important climate feedback processes like the ice ocean albedo feedback. But other users like mariners or ship captains say that the area fractions of multiple ice thicknesses or flow sizes are really not especially useful for navigation. They care more about the locations of the high sea ice pressure, as an example. But the sea ice models do have a lot of the things that they would like, just not so much in the detail that they want it. The models have gotten pretty complex over the years, and they're able to represent all kinds of different processes. So this schematic on the right describes most of the physics in the state-of-the-art sea ice models that can be represented within a single grid cell. So this is the column physics. And indeed, it is most of the physics in the model. There's thermodynamics like melting and freezing. There's hydrologic properties of the ice. There's such as, liquid water on top of the ice. Those are the melt ponds, and the liquid water percolates through the ice. And there's also morphological changes associated with ice deformation and ridging. Some of the other processes that you see in the air up above the ice occur in the atmosphere and the ocean components for the ones that are below the ice. But the sea ice model must still take them into account as part of its energy balances. So what's not in this column physics schematic is the large scale motion of the ice. And that's what I'm showing there on the left. The sea ice models need to get this motion right in order to have the right reflectivity, that very high albedo in the right places on the planet. So as the ice is moving, it's deforming. And one of the biggest challenges for sea ice models is getting the ice material to behave the way it's observed. For climate scales, like the Arctic basin that's shown here, again, we're looking down at the basin, and in the plot on the right, I've labeled Alaska and Russia to orient you a little bit. But for these scales, we model the ice as a viscous plastic material that yields or deforms once the strain on the ice gets big enough. So the right plot are the satellite observations, and then the left 4 plots are 4 different models with different resolutions. The lower resolution models, like the one on the far left, really have no hope of resolving these fracture patterns, but they can still indicate areas where there is activity. The higher resolution models do better, but they still miss a lot of the detail. And for reference later, we refer to these fractures as linear kinematic features, or LKFs. And they indicate where the ice is shearing and either producing ridges or else producing open water, which we call leads. Now, this is really important for operational users who want to know where the ice is weak or where it might be converging. So the US Navy has implemented my sea ice model, CICE, for its global ocean forecast. And the grid size in the Arctic is about 3.5 kilometers, which is pretty small by climate modeling standards. And they use information such as the strain rates to assess risk for their operations in the Arctic. So this example on the right was for a field 2018 called ICEX. And a similar kind of forecast is made by the Canadian Center. This one is showing ice pressure and velocity on the left. And the pressure, which is the color, indicates how strong the ice is. And it's somewhat correlated with the ice thickness, which is shown on the right. The resolution in this model is right around 4 kilometers also. And it picks up a web of these linear kinematic features in the ice. This forecast was made for the Mosaic expedition, which is the red dot that you see there at the time of that forecast. And I don't know if you've seen any of the news feeds about Mosaic, but it's a ship that they sailed up to the ice and moored to an ice floe in order to make measurements over the course of a whole year. So Los Alamos National Lab has a team up on the ship. They took about 50 instruments up there, and they've been making measurements. And the ship has been drifting since last September. It started about 85 north, where you see the black dot up there. And the COVID pandemic started after they were already up there. So the crew rotation since then have become rather challenging. For the last one, the ship had to leave the ice and rendezvous in Svalbard with another ship with a new crew. That's what the little leg is down at the bottom. And then they sailed back up to the ice pack to finish their drift. The dates that you see, December, February, April, June, and August, those are the dates, or those are the indicating the area within the pack where they expected the ship to be at those times, if the ice pack were normal. And as you can see, they have already drifted all the way out of the ice pack in Fram Strait, and then they sailed back north in order to continue measuring the ice during the freeze-up season. So the lesson there is the ice is actually moving much faster than they anticipated. Mosaic did use models for its planning purposes, and of course that had to begin several years before the ship actually sailed. And since they planned to drift across the Arctic Ocean, they needed information on pretty large scales, up to 1,000 kilometers. But generally, long-term planning can only use the larger scale information. That's because the sea ice is highly influenced by the weather, and so we can't predict the details very well. simply because we can't predict the weather that far out in any detail. But on the other hand, ship captains need much shorter term and much smaller spatial scale information, preferably less than 300 meters when they're actually out there. So we've developed the CICE models using fundamental physical principles, and these work very well for the larger scales in an average or a climate sense. But to get these short-term predictions correct, you have to start with the right initial state. And this is related to the plot I showed you before, that the ice thickness is critical for getting the area coverage right. That's even more true for very short-term predictions. So a challenge for Earth system model predictions is that the sort of transition time period from these very short time scales that are largely controlled by memory of the initial conditions to longer time scales at which the model's response to the external forcing emerges. So we are continuing to develop the model, but we're trying to do it in a way that is useful for the operational centers. On this slide, I'm showing some examples of areas of active research. The surface properties like snow have a very large impact on the albedo, which is critical for the ice area. Melt ponds also form on the ice surface. You can see those as the kind of brighter blue in the picture. And these also, because they're not white, they're darker, they also impact the albedo. They are very important for the longer term evolution of the ice pack, but really a lot less important for short-term predictions, except when the feedback makes the ice melt away completely. And that's what's happening in that kind of dark blue area just to the left in the photograph. That's where a lead is melting through. So these kinds of thermodynamic processes are very easily represented within a grid cell column. And so they're easily shared for all kinds of different applications. The challenge really is getting the atmosphere and ocean impacts right, because they do affect both the thermodynamics and the dynamics. So for example, waves and the flow size distribution affect both the albedo and the ice strength, which is important for the dynamics. So in the next few slides, I'm gonna mention some of the dynamic processes along with some new technology directions. So I'll start with this one, the sea ice ridging. As the ice flows move around, they crash into each other and buckle up into ridges. The fundamental concept in the standard ridging scheme that's employed by many sea ice models is that as the ice converges, its kinetic energy is converted into the gravitational potential energy of the ridges. From a theoretical point of view, that makes a lot of sense, but it doesn't actually work very well. So Andrew Roberts, who is at Los Alamos, went back to first principles and he just rethought the whole sea ice ridging process using the fundamental concepts from Lagrangian and soil mechanics. So for instance, the sea ice ridge, which is above sea level, and the keel, which is below it, both form hills of ice blocks that are, broken up from the sea ice flows. And these blocks are in hills that have an angle of repose, sort of like a pile of sand, but they're floating in seawater, one on top of the other, and that makes it a lot more interesting problem. But figuring out what that angle of repose is a minimization problem. And as it turns out, the comparisons with data using this formulation are really fantastic. So the keels under the ridges are important for pinning sea ice to the bottom of the ocean in kind of shallow water or continental shelf areas. And this is what creates what we call landfast ice. This is where the sea ice is locked in along the coast, and it's very difficult for the ships to get through it. Instead, it's used as a coastal highway for snowmobiles. So the standard configuration without this parameterization is not able to capture the landfast ice as observed. That's what's in the red circle there. What may look like dots are supposed to actually be motion vectors. So the ice is moving in there, and the observations are in the green circle for that area. What's missing is the grounding of the keels from large pressure ridges in these shallow water areas. So this new parameterization estimates the thickest ridge in a grid cell, and if it's thick enough to actually reach the seafloor, then a basal stress term is added to the momentum equation. And that term depends on the weight of the ridge above hydrostatic balance. And it turns out that it works very well in the area that I've got circled. Just to the lower right of that circle is an area between the mainland and an island that the model still doesn't capture very well. And so in order to do that, the Canadian team that developed this had to increase the tensile strength of the ice a little bit. But when they did so, the parameterization turns out to work remarkably well. This slide shows the frequency of occurrence of landfast ice in the observations on the left and in the model on the right. This parameterization is very useful for operations because, you know, ships have a hard time penetrating these areas where the ice is solid. And so the Canadians and now other groups are starting to use this in their operational forecast models. At the other end of the process spectrum, the sea ice is not solid. It's broken up into ice flows, like you can see in the satellite image that's looking down at the Bering Sea. And we've also recently implemented a joint flow size and ice thickness distribution in the model. And this allows the flow sizes to emerge naturally based on physical processes. This flow size distribution is particularly important now that the Arctic ice pack is starting to loosen up and waves can actually penetrate further into the ice. And this causes changes in the heat and moisture exchanges between the atmosphere and the ocean. And of course, those then feed back on the ice. Now, in terms of technology, the Department of Energy has been developing a new Earth system model called E3SM. It's the Energy Exascale Earth System Model. And it's being developed specifically to take advantage of the advanced computing architectures like GPUs that are available in DOE. The cool thing about E3SM is that the ocean and the ice components are formulated on an unstructured grid. And so the resolution can be focused wherever you want it. The plot that's on the right gives you some idea of the resolution around the Mertz Glacier. And it shows ice built up in front, that's to the right of the glacial tongue, and Pollinia downstream of it. And if I had a cursor, I could point that out on the Antarctic animation that you see, but it's down basically on the bottom, just kind of above the A. So an example where the resolution matters is for the potential shipping routes through the Arctic. The plot on the left here shows the northern sea route, which is in blue, and that's running along the Siberian coast, and the Northwest Passage in red, which runs through the Canadian archipelago. There are several options of paths through the islands, but as you can see, the lower resolution models, like the version 2 of CESM, have those islands in the Canadian Arctic connected either to each other or to the mainland. And so there's actually no way to sail through there in the model. And even the early version, the first version of E3SM, had one potential route for the Northwest Passage. And that's since been corrected in version 2 of E3SM because we can focus more resolution in the islands there. But nevertheless, we did some analysis of how the sea ice conditions are changing along both of those routes. and comparing two time spans. So to orient you, there's plots on here. The Northwest Passage are the four colored plots on the left. The Northern Sea Route are the four ones on the right. The columns are time spans. So on the left you have 79 and 99, and on the right of each of those are 2000 to 2014. And then the top and the bottom rows are sea ice concentration and sea ice thickness. The colors are for different months of the year, and the vertical extent, if you will, of those colors show the range of variability from ensembles of simulations. These plots, let's take September as an example. We see less sea ice cover in September, that's the yellow one, in the recent years, and it's thinner along both routes. One of the things that we learned in this project is that these various models, which is E3SM along with 3 different configurations of CESM, these models produce very different ice conditions. The small plots that you see here are their ice thickness for individual ensemble members. And the diagram at the lower left illustrates how well they match the observations, both in the state variable and in the variance. You want your model to be as close to that blue dot at the bottom as you can. So the best results are from the DPLE, that's Decadal Prediction Large Ensemble of CESM, and it is reinitialized each year. But interestingly, the results 9 years out from an initialization really do better than the first year results. We don't understand that, but it could have something to do with changes in the longer term climate forcing just showing up in the simulations. So anyhow, these are the kinds of analyses that we can do with the climate scale models. Now, short-term forecasts are considered an initial value problem. And so we do use data assimilation. The data assimilation can ingest data from a variety of sources, such as ice concentration from satellites. Satellite data really is best because it's large scale and it's also frequently available. There are some other data available, like in situ measurements, and those are used when they're available, but that's not all the time and not everywhere. A real problem here from a sea ice modeling perspective is that the data assimilation can make the model physics just completely irrelevant. And even worse, it can change the model's natural state so much that the processes and the feedbacks are unrealistic in the simulation. These models do have biases and a preferred solution that they want to go to. They relax to that model attractor. And that relaxation can actually skew a forecast, even on short timescales. The other thing that the other thing is that the atmosphere and ocean forcing truly dominate the details of the sea ice physics, really on all timescales, but especially short ones. By the forcing, I'm talking about winds and currents, the temperatures, the radiation. And for forecasts, this information often comes from atmosphere and ocean models, which have their own biases. So this is definitely a challenge. I'd say one of the more fundamental challenges is balancing this need for data assimilation, which is only available in the past and for the immediate present, balancing that with the physical modeling that's needed for prediction. And that challenge is perhaps even more important for atmosphere and ocean modelers than it is for the sea ice modelers. As I mentioned earlier, the timescales between the very short term and the very long term simulations are particularly challenging because they're influenced by both the initial condition and by the physical response to the forcing changes. And also, climate modelers and operational forecasters need different things. Climate modelers require conservation, and data assimilation makes conservation impossible. Mariners, like ship captains, want probabilistic risk analyses for particular quantities. I've listed a bunch of them here. And we have these quantities in the model, but as I said before, it's usually not at the detail that they need. And also, operational centers really need a stable and efficient, very trustworthy code base. So they prefer to keep the status quo for the near future, but they do need to incorporate improvements over time. So for climate modeling, big changes are not really needed. The climate models are pretty good for the standard scales that we use. In that sense, evolution is sufficient. But for fine scale forecasts that are needed by the mariners, we really do need a modeling revolution. There are a number of things that are common across all of these communities, such as computational efficiency, the column physics, we all need measures of uncertainty, and also the atmospheric and oceanic processes that are responsible for sea ice change. Sharing our codes through a common modeling framework allows a hierarchy of configurations that can be used for both research and operational needs. And the best part of an inclusive framework is that the research code developers contribute more directly to operational forecasting needs. That is, the code changes can get in faster, while the operational centers can provide validation guidance for the developers. And so this is the idea on which the CICE consortium is based, and it has been working pretty well so far. Looking to the future, the Department of Energy is funding development of a discrete element modeling approach for sea ice dynamics. This is a very promising and also very revolutionary candidate for the ice pack, which is heterogeneous and anisotropic at fine spatial scales. The sea ice or CICE column physics can still be used for each discrete element, and the elements can be pushed onto accelerated processors such as GPUs in order to increase the computational efficiency. Going a step further, a discrete element model could be embedded within the variable resolution mesh in E3SM and that would provide an even higher resolution where it's needed. So combining technologies like this is a very promising new direction that could bridge the operational needs for small scale details and large scale computational challenges. So to answer the question in the title, I'll say maybe. The question was, should sea ice modeling tools designed for climate research be used for short-term forecasting? And I do say maybe. Sea ice models developed for climate are already being used operationally, at least for the larger time and space scales. But we need improvements to capture the very fine scales that are needed by the mariners. This work is underway, and I'm very excited about the broad collaborations that are developing between the research scientists and the operational community for the benefit of both. And I will stop there and take any questions.
Thank you very much. Thank you, Elizabeth.
No, thank you.
Thank you. I'm very intrigued because the challenges or the differences you point out in regard to the requirements for forecasting and climate modeling, that rings very true to the challenges that I'm facing and that we're facing in terms of a seamless approach, that is methods that work for both weather forecasting and also climate modeling. So you have really spoken out of my heart in that
Oh,
regard.
good. Yes.
For our panelists and attendees, please post your questions into the chat. And while you do this, I have a few questions that I'm interested in. So it was interesting to me. I know very little about sea ice modeling. So you said it had a resolution of 3.5 kilometers. I would be really interested, is this the resolution that CSM uses it at?
No.
And, okay. And so I'm really interested in if you could comment a little on the non-homogeneities within a single grid scale in the different models, both forecasting and climate models, and if what are good approaches to representing this non-homogeneity, for example, stochastic approaches.
Oh, okay. Well, yeah, the CESM resolution is more like 1 degree,
Okay.
which is big.
Yeah.
They are doing some runs with higher, like 1/10 of a degree, and I can't at the moment convert that to kilometers, but the very high resolution is what the operational centers are doing, like the U.S. Navy. Let's see.
The question was, how can you represent non-homogeneity? Do you think bulk representations are sufficient, or do you think something like a stochastic approach might be a way forward in these coarse resolution climate models?
I think, you know, stochastic approaches have always been an intriguing idea for me. That's not something that I know anything about. You know, to a certain extent, the ice thickness distribution is sort of getting at that. It is a distribution, you know, it's a probability distribution. We're just discretizing it very, very coarsely with just 5 categories. You can discretize it more, but I'm not sure that you really gain anything by doing that. But again, it depends on what the question is that you're asking. And so for climate modeling, we have discretized it and used it really to be able to capture that ice ocean albedo feedback and other similar feedbacks like that are dependent on the thinner versus the thicker ice being within a grid cell. For the needs of the operational community, I think that stochastic approaches could be really a lot more useful because it could provide actual probabilities for things that they care about. You know, we're giving the probability of ice being of a certain thickness, but they don't care about that. You know, they care about what the strength is, right. But the strength is a what would you call it? It's kind of a combination of everything that's going on in the ice thickness distribution. It's not a quantity specific to a particular thickness category.
Right.
So you have to think about it in a different way.
And I guess the question is also spatial coherence. If you have spatial coherence, let's say in a 100 kilometer squared grid box, if that changes the ice properties as opposed to, you know, if it's not coherent and just totally dispersed. And
right.
My guess is, not being an ice modeler, that it changes in terms of ice growths and thickness growths and volume growths.
Yeah.
As opposed to a disparate one where maybe the melting takes a bigger role.
Yeah, that is true. For the climate modeling, I think I didn't say this explicitly, and I probably should have, but within a grid cell, we capture the area coverage as a fraction, which is the sum of the fractions of all those ice thickness categories. And that's fine for climate modeling because we really are interested in the average behavior, let's call it.
Fluxes, no? I mean, it's mostly fluxes as the other components see it.
Right,
yeah.
Right. But the question that continues to come up is that we're using this viscous plastic approach for the ice dynamics, which does bring in these linear kinematic features, which look like leads and ridges and that kind of thing. They're,
right.
I think, you know, qualitatively, that's essentially what you're simulating, but you're not simulating them in a realistic way at all. And especially when you get out near the ice edge, the ice flows are kind of few and far between. And that's definitely not a viscous plastic regime. And so that is a lot of the driver for going to these discrete element models, because you can simulate those regions where the ice flows are not just solid packed much more realistically.
Mm-hmm. Thank you. Is there any questions from the attendees? Please post them if you have any. Otherwise, I will ask more questions. You actually commented on this. You alluded to sort of the importance of resolving just orography in the Arctic regions and how that relates to systematic model error. You had a plot about it. I was wondering if you could tell us a bit more about how important it is to represent high resolution orography and sort of areas where all of a sudden you can have a through flow as opposed to a blockage. I think you showed a plot about this, but if you could talk a little bit more about it, I'd appreciate it.
Okay, I'm not sure which plot you're talking about, but
all right.
That's okay. This again is another place where, as climate modelers, we haven't really worried about those details. As long as we got kind of the large scale average behavior, it was good enough. But there are groups of users or modelers who are really interested in things like ice arches and what's going on in a particular polynya in a particular place on the, you know, along the coast or someplace like that. And in those cases, then the details of what's going on with the sea ice does matter a lot more. And again, I think that's the research area right now, is figuring out how to represent those things. How much detail do we actually need? You know, how complex does the model need to be in order to answer the question that you have? And, you know, so far we haven't needed those kinds of details, but it seems like we're being asked that kind of thing more and more. So people are working on those aspects of the model.
And it seems it plays CICE plays a major role in terms of teleconnections, like NOA teleconnections in their interactions with the stratosphere and large scale phenomena like that.
Yeah.
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 Yeah. Thank you, sir. I really enjoyed your talk very much.
Thank you.
If there's any other questions, this is the last chance to post them. Otherwise, I'm sure you can email Elizabeth if you have any more questions. I thought it was very inspiring. I would love to talk more with you.
Okay. Great.
About inhomogeneities and the impact of not resolving them. Yeah.
Yeah, sure.
And that, thank you so much. I really liked your talk, and I wish you a very nice evening.
Thank you very much. Just shoot me an email if you have any questions.
Okay, thank you.
Thanks.